let's suppose that we have a graph, and on the x-axis it has the speed in meters per second, and this is the speed of the particles of an ideal gas. And on the y-axis we have the fraction of particles at that speed. So let's say that goes, let's say 200, 400, 600, 800, 1000, and so on. Now, the way that it looks like is that it's not all of the particles, for example, that will have a speed of 1000 meters per second. So you don't see like a peak here. What you see instead is a little curve, and that means, for example, that the particles in the gas have different speeds, but most of the particles, they have a speed of about, in that case, 220 meters per second, right? If you have a hotter gas, maybe then the curve will be maybe like this. That means surely the gas is hotter because most of the particles are now moving at higher velocities, right? That's what this means. So we define the root mean square speed. Let me write that here. So we say root mean square speed. By the way, sorry for my voice. I am sick. That's not great, but that's how it is. So the root mean square speed, and we notate it with c. And we say that c is the square root of the speed of one particle squared and the speed of the other particle squared, and we add them up generally. If we have n particles, we add the square of their velocities, and we divide by n the number of particles that we have. And now you will be wondering, why does it make sense to define a root mean square speed? And it's actually because when we calculate the average kinetic energy of n molecules, so this is the average kinetic energy of n particles, n molecules, whatever you have, the way we do it is we say, well, Ek is a half times the mass of the first particle, V1 squared, plus a half times the mass of the other particle, V2 squared. We're talking about the same substance, so the particles have the same mass, so a half m Vn squared. And if we factor out a half m, then we have V1 squared plus V2 squared plus all the way to Vn squared, which is a half the mass and times the root mean square speed. There you go, to the power of 2. So that is what we define as the root mean square speed. Now we can use this if we want to, and this formula is given to you, and there is a proof behind it, but I'm not going to bother now. So P, which stands for the pressure in pascals, is a third times rho. Watch out, this is not pressure, this is a rho, and this is the density in cubic meters, times the speed that we just saw to the power of 2, and this is C is the root mean square speed, and it has units meters per second. So we could actually find the pressure if we know the density and we know the speed as well. Now the kinetic energy, like we have seen before, is Ek here, is a third times Kb. Kb is a constant times the temperature. You could, if you wanted, maybe I'll show it here. I'll make some space. You could, if you wanted, you could write a half times the mass of one particle and the root mean square speed to the power of 2 is equal to 3 over 2 kBt. So you could, for example, you can cancel out the 2's and you can see the root mean square speed can be written as perhaps the square root of 3 kBt divided by the mass. And this is the average speed per particle in a way, even though that's not totally correct. That's what it stands for. So we could, let's just put it in a nice blue box. And also, yeah, you know all this formula, right? Now, you have also worked plenty of times with the equation of state. We also worked with it before. And instead of, this is the number of moles, n. Instead of writing n, we can write the number of particles in the substance over the Avogadro constant. And then you can convert the formula to this right over here. And if you combine R divided by Na, they're both constants. R is the gas constant and Na is the Avogadro number. So they combine to Kb. So Kb is another constant. And I will show you right away where to find it. So if we go back at the... Yeah, that's your formula booklet. And you can see the Boltzmann constant Kb is this much. And the Avogadro constant is this much. So let us get back to where we were, which was here. Now, you could write this as let's see, 2 seconds. You could write this as P times V equals NKBT. So you're also allowed to write the equation of state this way because R over Na, they form that Kb, the other constant. Okay, now the internal energy of an ideal gas, we notated with U, internal energy. And in the past, we've learned that the internal energy is equal to the sum of the kinetic energy of all of the particles in the constant plus the potential energy of all, the particles in the substance. However, we talked about ideal gases, and an ideal gas is defined in such way that the potential energy that it has is 0. So for ideal gases, the internal energy of the particles is equal to just the kinetic energy of the particles. And we saw here, this was the kinetic energy, the average kinetic energy per particle of the substance. If we want to find the internal energy, which is the sum of all of the kinetic energies of the particles in the substance, then you're going to have to multiply the whole thing by n. So U, the internal energy, is n times the average kinetic energy per particle. And you could rewrite this in a number of ways. This is the second way that you can rewrite this, considering that n times Kb equals to nr. Or you could also write this in the third way that I have here, which is PV. Because according to the equation of state, PV is equal to nRT, right? So this is a bunch of equations that you have here. And I would like you to comfortably navigate around them. If you look at the formula booklet, let's go and have a look at the formula booklet. The formulae that you're given in this chapter are those. So the first one is that the pressure is force over area. The number of moles is the number of particles in the substance divided by the Avogadro number. And then you're given the equation of state, PV equals nRT, or you could write that as PV equals NKBT. That's the same thing. This is the pressure, like I showed you before. This is the density. And Tsokos uses the root mean square speed. Tsokos writes it as C. In the formula booklet is given as V. You do as you wish, okay? I like the C because then you will not confuse the speed. This is speed and this is volume, right? So Tsokos writes it as C, so you don't confuse speed with volume. And lastly, this is the internal energy of the particles, which is the sum of all of the kinetic energy of the particles in your substance. So, now that we have all of the theory cleared out, I will go with you and answer the following questions. And here. So, those questions here is a good idea that we solve them all. So 23, it says helium has a molar mass of 4 grams per mole, and neon has a molar mass of 20 grams per mole. The helium and neon are kept at the same container, and you have to find the ratio of the kinetic energies. Well, for A, if you want the kinetic energy of, let's just write it as EK, and then you have helium. Well, that is equal to 3/2, as we learned just now, kBT. And if you have the kinetic energy of, what's the other substance? It's called neon. So you have neon here. It's also 3/2 kBT, because it says that they are kept in the same container, and therefore they have the same temperature. So if you find the ratio of the two kinetic energies, the ratio will be 1. So EK for helium, the average, divided by the average kinetic energy for neon particles, that's going to be 1, because they're at the same temperature. In B, it says find the average root mean square speeds of the molecules. And like we've worked previously, I'm just going to steal those equations that I just wrote above so I don't have to write them twice. So I'm going to do it this way. So a half times the helium mass times the speed squared, right? That's the kinetic energy of the helium particle, and neon times the neon root mean square speed. And if you divide those two equations, you will find that the ratio of the two speeds and the ratio squared, as you can see, let's see, if you divide those two equations, those cancel out because they're at the same temperature. The halves cancel out, so the ratio of the two speeds squared is equal to the mass of the neon divided by the mass of the helium. And now, if you want to apply the square root on both sides, the speed of the helium particles divided by the speed of the neon particles, the average speed in any case, is going to be equal to the square root of. We don't know exactly what's the mass of a neon particle, but we know that the mass per particle is equal to the molar mass divided by Na. This is because the molar mass, it gives us the mass per mole, while the Na, the Avogadro number, it gives us how many particles we have per mole. Therefore, if you want to find the mass per particle, you have to divide those two numbers. So M will now be the mass that you have per particle. In this question, we are actually given only the molar mass. So we're going to have to write this as the molar mass of neon over Na divided by the molar mass of helium. The helium is meant here to be an index of helium over Na. And when you do this calculation, you will find that this is equal to the ratio of the molar mass of neon over the molar mass of helium, which is the square root of 20 by 4, which is the square root of 5. So, I hope this helped. So for B, the answer is square root of 5. And for A, question 23, the answer is 1. Now, let's move on and let us answer question number 25. So 25 says, a gas is kept at a pressure of blah, and the density is this. What is the root mean square speed of the molecules? Well, this is straightforward. The pressure is 1/3 times the density, as we learned, times the speed, the root mean square speed to the power of 2. So if you use this formula, and I'm going to do it probably, where is a good spot? Maybe here. So for 25, you're going to have that P equals a half rho C squared. And you want to solve for C, which is going to be the square root of 3P over rho, which is square root of 3 times 2.8 times 10 to the 5 pascals, divided by the density, which is 1.2 kilograms per meter cubed, and you will get roughly 840 meters per second. So this was the answer on 25. And let's move on. Let's go to 26. And I'm going to answer 26 on the question itself. So it says, the pressure and the volume of a fixed mass of an ideal gas are both doubled. So you double, PV equals nRT. And what happens is you double both the pressure and the volume. When you double both the pressure and the volume, so you get 2 here and 2 there, the temperature on the other side will become 4 times more. So, let's write it this way. If pressure and volume become 2 pressures and 2 volumes, then the temperature will become 4 times the old temperature, okay? But it's asking what will happen to the root mean squared speed of the molecules. And we just learned that a half mc squared, the average kinetic energy per particle, is equal to 3 over 2 kBT. So you can see, if the temperature becomes 4 times more, c squared will also become 4 times more. And if c squared becomes 4 times the old one, that means that c will become twice the old one. So what happens to the root mean square speed of the molecules? We say that so c is doubled. And then B, what happens to the internal energy? Well, we have seen that the internal energy U is 3 over 2 nRT. We just saw that, right? So when the temperature becomes 4 times more, U will also become 4 times more. So you can say that what will happen to U, it will be quadrupled. U will be quadrupled, okay? All right, let's move on to question 29. And I wish I had a little bit more space so I could read the actual question. Question 29 says, calculate the root mean square speed of krypton atoms at the temperature of 350 Kelvin, and it gives you the molar mass. I will just show you what I did before. So half times the mass times the root mean square speed squared equals to 3 over 2 kBT, right? And this is the mass per particle, and here we're only given the molar mass. And as I explained right before, if we want to use the molar mass, instead of m here, use the molar mass, which is how much mass there is per mole, divided by how many particles you have per mole, Na, and then you will be good to go. So let's see, kBT, and you can actually isolate C here, and if you isolate C, how will it look like? C will be equal to the square root. See, the 2's cancel out. So it will be 3 times kBT divided by the... it will be divided by what? The molar mass mu? Did I do it correctly? Let me have a look. 84... I forgot something. I think I forgot the Na here. There you go. That's correct now. So it would be 3kbt times NA divided by mu, and that way you will calculate the root mean square speed, and you will get about 320 meters per second. I recommend that you also look into 32 and perhaps 31. Not so much into 30, but yeah, you're welcome to look into 30 as well.